In the year 2017, a discovery of extraordinary proportions unfolded before astronomers. An interstellar visitor, subsequently christened Oumuamua, breached the boundaries of our solar system. Its velocity was remarkable, its nature enigmatic, its very existence a challenge to established expectations. 2 years later, a second interstellar object, Comet-2 Borisov, served as compelling evidence that Oumuamua's arrival was no mere coincidence, no isolated event. Now, in 2025, history has repeated itself. A new celestial body has materialized on our astronomical radar, designated 3I Atlas. Unlike Oumuamua, whose detection occurred 5 days after its closest approach to Earth, this time we were prepared. Discovered on July 1, 2025, and duly catalogued by the International Astronomical Union's Minor Planet Center, 3I Atlas immediately sparked considerable interest within the astronomical community. Its initial appearance was on the Near-Earth Object Confirmation page, flagged for further investigation. But this was no ordinary space rock following a predictable elliptical trajectory. The moment astronomers commenced trajectory calculations, the evidence became irrefutable. This object was not a native of our solar system. Prepare yourselves. The narrative commences. On July 1, 2025, astronomer Larry Deno submitted data on what initially seemed an unremarkable space rock. The object presented as a faint point of light against the backdrop of stars, magnitude 18.8, over 2 million times fainter than Polaris, the North Star. Yet this dim point was in motion, not the languid drift of a typical asteroid, but a movement characterized by urgency, a sense of purpose. These preliminary calculations caused Deno to hesitate. The object's velocity strongly indicated it was not gravitationally bound to our Sun. Imagine a baseball thrown with such force that it overcomes Earth's gravitational pull completely, never to return. Atlas operates as part of a global surveillance network designed to safeguard Earth from potential cosmic threats. Every night, its high-powered cameras capture images of the same celestial regions, comparing newly acquired photos with previous ones to identify any movement. Most detections prove to be main belt asteroids, following predictable orbits or near-Earth objects on well-understood paths, posing no imminent danger. The system processes thousands of observations nightly, flagging objects for human scrutiny based on their motion and brightness characteristics. When Deno reviewed the latest dataset, one particular object stood out, not for its brightness or size, but for its unexpected movement. Within hours, observatories worldwide were focusing their instruments on this enigmatic visitor. The Minor Planet Center classified it as a near-Earth object, initially catalogued as A1PI3Z. The designation seemed routine, yet the underlying numerical data told a different tale. Initial observations originated from telescopes in Arizona, where the Catalina Sky Survey team swiftly confirmed the object's unusual path. David Rankin obtained clear images, depicting the visitor as a distinct point of light traversing the starry backdrop. His photographs became some of the earliest documented records of this cosmic traveler. As observations flooded in from global facilities, the picture sharpened, revealing something extraordinary. This object was traveling at 66 kilometers per second relative to our Sun, far exceeding the 42 kilometers per second escape velocity of our solar system. Its speed surpassed that of any known asteroid or comet, suggesting it did not originate within our system. The European Space Agency's planetary defense team immediately took note. Their telescopes in Spain and Chile began tracking the object, providing crucial data points for precise trajectory determination. Each new observation refined the calculations, bolstering the evidence for something truly remarkable. Excitement rippled through the astronomical community. Could this be another interstellar visitor, similar to the enigmatic Oumuamua that captivated the world in 2017? Trajectory calculations pointed to something even more exceptional. This was not just another interstellar object. It moved faster and followed a more extreme path than any previously detected visitor. Professional astronomers requested emergency telescope time, sensing a once-in-a-generation discovery. Amateur observers shared coordinates on social media, creating a global network of sky watchers to assist in tracking this cosmic messenger. Subsequently, we delve into the moment astronomers recognized they were witnessing something unprecedented. The breakthrough occurred when citizen scientist Sam Dean investigated archived telescope data. Working late into the night at his home computer, Dean systematically searched through weeks of Atlas observations, seeking earlier glimpses of the mysterious object that had recently captivated global attention. His persistence yielded spectacular results. Deep within the archives, Dean discovered clear images of A11Pi3Z dating back to June 25th. These were not random, fortunate captures, but a systematic series of observations that had remained unnoticed in the data for over a week. Each image showed the object progressing along its path, a cosmic breadcrumb trail awaiting discovery. These pre-discovery observations revolutionized astronomers' understanding of the visitor. With 6 full days of tracking data, instead of mere hours, orbital mechanics calculations became significantly more precise. The margin of error diminished from broad estimates to mathematical certainty. Using this expanded dataset, astronomer Ya Kwanji located even earlier observations from the Zwicky Transient Facility, dating back to June 14th. The trail now extended across nearly 3 weeks, providing an unprecedented baseline for calculating the object's actual trajectory through space. The refined calculations yielded figures that stunned seasoned astronomers. The object's eccentricity measured 10.4, plus or minus just 1.1. Astronomically, this number represents something almost inconceivable. Earth's orbit has an eccentricity near zero, meaning we travel in a nearly perfect circle around the Sun. Even the most elongated comets in our solar system rarely exceed an eccentricity of 3. An eccentricity above 1 indicates a hyperbolic path, entering our solar system once and never returning. But 10.4 represents something extraordinary. The highest eccentricity ever recorded for any object passing through our cosmic neighborhood. Imagine a stone skipping across a pond, except this stone is so fast it barely touches the water before launching into the air, never to return. The mathematics presented an unambiguous narrative. The object followed what astronomers term an unbound trajectory, confirming beyond any reasonable doubt its interstellar origin. This was not a long-period comet returning from the Oort cloud or an asteroid ejected from the main belt. This object was genuinely alien to our solar system. Professional observatories worldwide immediately grasped the significance. The International Astronomical Union, acting with unusual swiftness, officially designated the visitor as 31 Atlas, making it only the 3rd confirmed interstellar object in recorded history. The Roman numeral 3 marked its position in this exclusive club of cosmic wanderers, while Atlas, the survey telescope that first detected it, lent its name to this object. The designation held immense significance. Astronomers now possessed mathematical proof that objects from other star systems routinely traverse our cosmic neighborhood, silent emissaries bearing data about distant worlds and alien planetary systems. Yet this visitor harbored even more astonishing revelations. Its unprecedented velocity through our solar system, a speed that fundamentally reshapes our comprehension of interstellar travel, was the first. At 66 kilometers per second relative to our Sun, it surpasses all prior interstellar visitors by a considerable margin. To illustrate this phenomenal speed, one could journey from New York to Los Angeles in under 2 minutes, or circumnavigate the Earth in less than 11 minutes. This extreme velocity narrates a tale of cataclysmic cosmic events that transpired millions of years ago within a distant star system. Such velocities are not achieved through subtle gravitational nudges or gradual orbital decay. Something immensely powerful propelled this visitor from its home system, initiating an epic, million-year voyage across the interstellar void. The physics underlying such extraordinary speeds involves catastrophic gravitational encounters with massive objects, close stellar flybys, or even the violent demise of stars. When a massive star explodes as a supernova, the tremendous energy released can hurl nearby objects at incredible velocities, essentially transforming them into cosmic projectiles hurtling through the galaxy at unimaginable speeds. Current astrophysical models posit that 3E Atlas has journeyed through the vast emptiness of interstellar space for millions of years, potentially since before the evolution of complex life on Earth. During this immense time frame, it has endured the profound cold of the cosmic void, with temperatures approaching absolute zero. While radiation from distant stars gradually altered its surface chemistry and structure, the object's inbound trajectory strongly suggests its origin within the galactic disk, the flattened plane where most stars in our Milky Way galaxy reside. This directional data offers intriguing clues about a stellar encounter that predates human civilization, a time when our solar system occupied a drastically different position relative to neighboring star systems. What renders this record-breaking speed even more remarkable is 3E Atlas's unwavering velocity as it approaches our Sun. Unlike objects originating within our solar system, which follow predictable elliptical orbits dictated by solar gravity, this interstellar visitor will retain its tremendous speed throughout its passage. It will execute a cosmic slingshot maneuver around the Sun, further accelerating before hurtling into the darkness beyond Neptune. The Sun's gravitational influence will subtly deflect the visitor's path, but it lacks the power to capture it into a stable orbit. 3E Atlas possesses far too much kinetic energy to be ensnared by solar gravity. Following its brief encounter with our star, it will continue its eternal galactic journey, carrying whatever secrets it holds about its enigmatic birthplace. This incredible speed also presents urgent challenges for astronomers striving to study this rare visitor from another world. The number 6.3 will forever define 3E Atlas in the annals of astronomical history. This orbital eccentricity represents the most extreme trajectory ever documented by human science, utterly eclipsing even the remarkable eccentricities of previous interstellar visitors, such as Oumuamua's 1.2 and Borisov's 3.4. Grasping orbital eccentricity demands a thorough consideration of the shapes objects trace through space-time. A perfect circle possesses an eccentricity of precisely 0, signifying the most stable orbital configuration imaginable. Earth's orbit, slightly elliptical, measures only 0.017, so near to circular that our planet experiences negligible variation in its solar distance throughout its yearly cycle. Many bodies within our solar system adhere to similarly predictable patterns. Even highly elongated orbits, such as Halley's comets, extending far beyond Neptune before its 76-year return, exhibit an eccentricity of merely 0.967. These are bound orbits, mathematical curves that close upon themselves, repeating endlessly. However, when eccentricity surpasses the critical value of 1, the underlying mathematics undergo a complete transformation. The object then follows not an elliptical path, but instead a hyperbolic trajectory, resembling the distinctive arms of a mathematical hyperbola extending infinitely. At 6.3, 3 Atlas follows one of the most open hyperbolic trajectories theoretically feasible, minimally affected by our Sun's gravitational field. This extreme mathematical value offers crucial insights into the object's tumultuous history. Such exceptionally high eccentricity typically arises from close encounters with immense gravitational sources, catastrophic disturbances accelerating objects, far exceeding their usual escape velocities. Imagine a marble gently circling a bowl's rim, then suddenly subjected to a forceful impact, launching it completely from the bowl and across a room. The precise trajectory calculations also pinpoint 3 Atlas's entry point into our solar system. It arrived from the constellation Sagittarius, originating near the galactic center, a region of exceptionally high stellar density. This inbound trajectory suggests the object may have interacted gravitationally with multiple stars during its extended interstellar voyage, each close stellar passage subtly altering its course. Astronomers can now forecast with exceptional accuracy 3 Atlas's movements during its fleeting visit to our cosmic vicinity. The calculations reveal it will reach perihelion, its closest approach to the Sun, on October 29th, passing just 1.4 astronomical units from our star. This distance places it safely within Mars's orbit, yet comfortably distant from Earth. Nevertheless, this mathematical precision generates profound new questions concerning the cosmic violence that forged such an extreme wanderer. Professional astronomers, engrossed in current observations and orbital projections, unknowingly shared the spotlight with unsung heroes in the 3I Atlas saga. These were amateur researchers, individuals driven by an extraordinary commitment to unraveling the cosmos's hidden secrets. Sam Dean, diligently working from his home, meticulously combed through archived Atlas telescope data weeks prior to the official announcement. His perseverance yielded spectacular results, clear, unambiguous images of the enigmatic object, captured from June 25th through June 29th, extending the observation window by several crucial days. This expanded dataset transformed initial, imprecise estimates into precise mathematical calculations. With a significantly longer time frame, astronomers could dramatically refine the object's orbital parameters, conclusively confirming its interstellar origin. What began as tentative hypotheses, based on limited information, solidified into irrefutable evidence of an alien visitor. Other dedicated citizen scientists contributed their own significant findings. Yewani systematically unearthed observations from the Zwicky Transient Facility archives, dating back to June 14th, while accomplished amateur astronomer Philip Romang obtained striking corroborating images using sophisticated remote telescope systems in Chile. Their collective efforts produced the most comprehensive tracking record ever compiled for an interstellar object. This unprecedented collaboration heralds a revolutionary era in astronomy, one where professional observatories and passionate amateur researchers seamlessly collaborate to unveil cosmic mysteries that might otherwise remain hidden. The proliferation of remote observing systems and publicly accessible data archives now empowers anyone with sufficient curiosity and patience to make genuine, impactful contributions to cutting-edge science. The citizen science movement also underscores how easily extraordinary celestial objects can remain concealed within massive datasets. 3I Atlas, in fact, appeared in multiple telescope surveys for weeks before its true extraterrestrial nature was recognized. Only through rigorous analysis and careful cross-referencing of observations did its remarkable interstellar identity finally emerge. This crucial detective work proved indispensable, as 3I Atlas nearly evaded detection entirely, effectively disguised against one of the most challenging observational backgrounds in the night sky. Without the dedicated contributions of these amateur astronomers, this cosmic visitor might have traversed our solar system completely undetected. The collaborative spirit demonstrated by these citizen scientists exemplifies the potential of distributed research and the democratization of astronomical discovery in the 21st century. 3I Atlas, a near-miss interstellar visitor, remained hidden for several crucial weeks within our solar system. Automated detection systems failed not due to its faintness or slow speed, but because of its exceptionally poor location for astronomical observation. Its orbital path directly intersected the galactic center, the densely packed core of our Milky Way galaxy. Imagine searching for a single snowflake amidst a blizzard. This illustrates the immense difficulty of detecting moving objects against the billions upon billions of stars forming that brilliant, overwhelmingly crowded backdrop. This area of the sky, towards the constellation Sagittarius, boasts the highest concentration of visible stars in Earth's night sky. The galactic bulge's extraordinarily dense stellar field renders distinguishing individual moving objects from stationary background stars nearly impossible. Automated detection systems, optimized for relatively empty star fields, struggle immensely in such visually chaotic regions. Sam Dean, the citizen scientist who ultimately discovered crucial pre-discovery observations, attributed the object's extended period of undetected presence to this cosmic camouflage. 3I Atlas blended seamlessly with the overwhelming stellar background, its subtle motion completely obscured by the visual chaos of countless distant suns vying for attention. The irony is profound. 3I Atlas arrived from the vicinity of the galactic center, potentially carrying invaluable scientific data on star formation and planetary system evolution from that incredibly dynamic region. Yet its origin amongst dense star fields rendered detection nearly impossible with current automated survey techniques. The galactic center presents observational challenges far beyond simple star density. Interstellar dust clouds scatter and absorb light, creating complex brightness and darkness patterns that confuse automated detection algorithms. Gravitational lensing effects from massive objects distort the apparent positions of background stars, further hindering identification of truly moving objects. Only after 3I Atlas moved away from the densest background stars did automated survey systems flag it as potentially unusual. By then, precious weeks of observational time were irretrievably lost, though fortunately, enough remained for comprehensive scientific study. This near miss underscores a crucial, previously unrecognized limitation in our current detection methods and survey approaches. When the enigmatic object Oumuamua first entered our solar system in 2017, it ignited fervent scientific debate and increasingly speculative hypotheses among researchers globally. Its peculiar, unexplained acceleration away from the Sun, highly unusual elongated form, and complete absence of visible cometary activity prompted some leading researchers to propose increasingly exotic explanations, including the genuinely controversial idea of an artificial origin. 3I Atlas presents a completely different, refreshingly straightforward narrative. This latest interstellar visitor behaves precisely as astronomers anticipate a typical interstellar comet should, adhering to completely predictable physics without any mysterious accelerations, inexplicable trajectory deviations, or other puzzling characteristics that might suggest exotic origins. Initial observational data revealed unambiguous evidence of normal cometary activity, perfectly matching theoretical predictions. Multiple telescopes detected a faint yet clearly visible coma, the characteristic cloud of gas and dust naturally surrounding active comets as they approach the Sun and undergo significant solar heating. The object also displayed a short, distinct tail, measuring only 3 arcseconds in angular length, definitively confirming its status as a genuine comet rather than an inert, rocky asteroid. The prestigious Nordic Optical Telescope observations by renowned astronomers, David Jewett and Jane Liu, provided conclusive proof that 3E Atlas was demonstrably active, steadily releasing gas and dust as solar heating impacted its ancient icy nucleus. This entirely normal behavior aligns perfectly with detailed theoretical predictions for how interstellar comets should appear upon entering a new star system after millions of years in deep space. Unlike Oumuamua's deeply puzzling reddish surface coloration and bizarre, cigar-like shape that defied simple explanation, 3E Atlas exhibits all the expected properties of a comet naturally formed in the cold outer regions of another planetary system billions of years ago. Its overall composition and behavior seem remarkably similar to comets found in our own Kuiper belt, strongly suggesting common formation processes across many different star systems throughout the galaxy. Detailed measurements from the Lowell Observatory's Discovery Channel telescope showed that the comet's surrounding coma displays a distinctly reddish hue, clearly indicating significant dust content, remarkably similar to the prior interstellar comet, Borisov, discovered in 2019. This important consistency strongly supports existing theoretical models of planetary system formation and evolution around diverse types of stars. 3E Atlas represents precisely what scientists hope to discover: more interstellar objects that can teach us fundamental truths about the universe through familiar, well-understood physics, rather than perplexing enigmas that challenge our basic comprehension of the cosmos's workings. However, this exceptionally well-behaved celestial traveler confronts the unavoidable constraint of a severely limited observation window. From the exact moment 3I Atlas received official confirmation as a genuine interstellar object, astronomers across the globe immediately engaged in an unprecedented coordinated effort. Every major terrestrial telescope facility urgently requested emergency observing time, acutely aware of the exceedingly narrow window of opportunity before this cosmic visitor vanished forever into the vastness of space. This pressing time limitation is a direct consequence of 3I Atlas's particular trajectory and unfortunate alignment with Earth's position. The comet will remain visible to ground-based telescopes only until September 2025, after which it passes perilously close to the Sun for safe telescopic observation. Intense solar radiation will then completely obscure the object until early December, when it finally reappears on the far side of our star, already commencing its inevitable departure from the solar system. Professional observatories worldwide, from Chile's Atacama Desert to Hawaii's Mauna Kea, are now dedicating their most valuable telescope time to studying this extraordinary cosmic messenger. The James Webb Space Telescope, humanity's most potent infrared observatory, has already begun directing its advanced instruments toward 3I Atlas to analyze its thermal emissions and detailed chemical composition with unparalleled accuracy. The European Southern Observatory's facilities dispersed across Chile including the acclaimed Very Large Telescope Array, are systematically monitoring the object's luminosity fluctuations and conducting thorough spectroscopic analyses. These essential observations will pinpoint the precise chemical elements and molecular compounds comprising the comet's ancient nucleus and active coma, yielding invaluable insights into the environmental conditions within its distant stellar birthplace. Ground-based telescopes face considerable additional technical hurdles beyond mere time constraints. 3I Atlas currently displays a magnitude of 18.8, demanding sophisticated equipment and exceptionally dark skies for successful detection. Although it might brighten slightly as it nears the Sun, it will never become visible to casual stargazers or amateur observers using basic equipment. This remarkable collaborative endeavor extends far beyond professional observatory facilities. Amateur astronomers equipped with advanced imaging systems are providing valuable photometric measurements, especially crucial measurements that track subtle brightness variations and assist in determining the object's rotation period and surface features. This extraordinary international collaboration showcases modern astronomy at its zenith, with researchers openly sharing data and meticulously coordinating observations to maximize the scientific yield from this exceptionally rare event. Never before have so many telescopes simultaneously trained their gaze upon a single interstellar visitor. The Lowell Observatory's Discovery Telescope in Arizona has been conducting nightly observations since the Discovery announcement. Observatories in Australia and South Africa provide essential southern hemisphere coverage as the object traverses different celestial regions. However, the genuine excitement stems from the remarkable discoveries these coordinated observations are already yielding. As 3E Atlas races steadily toward the inner reaches of our solar system, it undergoes a truly remarkable and unprecedented transformation. After spending millions of years in the profoundly frigid depths of interstellar space, this ancient comet is slowly awakening as our sun's increasingly intense energy finally reaches its primordial surface for the first time in eons. The very first indications of renewed activity appeared almost immediately following the initial discovery announcement. Sensitive telescopes quickly detected the gradual formation of a distinctive coma, the characteristic bright cloud of gas and dust that naturally forms when solar heating begins sublimating ancient ice deposits directly from the comet's nucleus. This captivating process transforms solid ice directly into vapor, bypassing the liquid phase entirely, a consequence of the vacuum conditions of space. The comet's newly formed tail, currently only 3 arc-seconds in angular size as viewed from Earth, represents precious material steadily streaming away from the nucleus under relentless pressure from solar radiation and the constant solar wind as 3E Atlas continues its approach toward the Sun over the coming months. This tail will almost certainly grow dramatically longer and more visually striking. What makes this cosmic awakening particularly intriguing from a scientific standpoint is that it represents the very first time in millions of years that this ancient object has experienced any significant heating. During its incredibly long journey through the vast emptiness of interstellar space, 3E Atlas was constantly exposed to temperatures approaching absolute zero, with only the extremely faint radiation from distant stars providing any measurable energy input. The dramatic transition from deep space cold to intense solar heating triggers remarkably complex chemical and physical processes throughout the comet's structure. Subsurface ice deposits begin sublimating at various depths, potentially exposing completely fresh material that has remained essentially unchanged since the comet's original formation billions of years ago in an entirely different star system. Sophisticated spectroscopic observations are already beginning to reveal the detailed chemical composition of the escaping gases and dust. These precise measurements will inform scientists exactly what molecules and chemical compounds are present in the nucleus, providing direct samples of pristine material from another planetary system billions of light-years away. The subtle brightness variations that astronomers are meticulously monitoring may eventually reveal how the nucleus rotates and whether its surface displays uniform composition. Some areas might prove significantly more active than others, creating dramatic jets of gas and dust as they rotate to face the sun during the comet's approach. This remarkable awakening process offers an absolutely unique scientific opportunity to study completely pristine material from beyond our solar system. The distinctly reddish glow now surrounding 3E Atlas tells an ancient story inscribed in cosmic dust particles, revealing precious secrets about its mysterious origin and its incredibly long journey through the cold depths of interstellar space. This subtle but unmistakable color signature provides crucial scientific clues about the comet's detailed composition and complex evolutionary history. Careful observations conducted by the Lowell Observatory's Discovery Telescope clearly show that the comet's developing coma displays a distinctly reddish hue, definitively indicating the presence of complex organic compounds and various dust particles throughout the surrounding cloud. This characteristic coloration closely resembles that observed around Borisov, the previous interstellar comet discovered in 2019, strongly suggesting fundamentally similar formation processes occurred in the cold outer regions of different planetary systems. The ancient dust, now being steadily released from 3E Atlas's nucleus, contains invaluable scientific information about environmental conditions in its birth system that existed billions of years ago. When planetary systems first form around young stars, the frigid outer regions naturally become populated with countless icy bodies, rich in water, carbon dioxide, methane, and complex organic molecules. These fundamental building blocks of planets and potentially life itself become incorporated into comets during the violent, chaotic early phases of planetary system evolution. Detailed spectroscopic analysis of the escaping dust reveals specific wavelengths of light that are characteristically absorbed and emitted by different chemical compounds. Each individual molecule possesses a unique spectral fingerprint, allowing skilled astronomers to identify water vapor, carbon monoxide, methane, ammonia, and increasingly complex organic species within the expanding coma surrounding the nucleus. The precise size distribution of dust particles also provides critically important scientific information about the comet's activity levels. Larger particles typically indicate very recent activity directly from the nucleus surface, while much smaller grains may have been gradually processed by cosmic radiation during the extended interstellar journey. The observed ratio between different particle sizes helps determine how geologically active the comet was in its original star system versus how much new material is being released now. Upcoming infrared observations will prove particularly valuable for studying the detailed thermal properties of individual dust grains. The James Webb Space Telescope can detect subtle heat radiation emitted by microscopic dust particles, revealing their precise temperature, size distribution, and chemical composition with completely unprecedented accuracy and detail. The European Southern Observatory's Very Large Telescope is conducting complementary studies using advanced polarimetry techniques to understand how dust particles scatter sunlight, providing additional insights into their shape, size, and internal structure. This cosmic dust represent some of the most scientifically pristine material we can possibly study from another star system. Next, we explore why this visitor appears dramatically larger than any previous interstellar objects. Ice from the comet's nucleus sublimates. This process directly transforms solid ice into vapor, skipping the liquid phase altogether. The comet's short tail, measuring only 3 arcseconds in angular size, displays material streaming from the nucleus, propelled by solar radiation and the solar wind. As 3I Atlas continues its approach to the Sun, this tail will probably lengthen and become more conspicuous. What renders this awakening especially captivating is that it marks the first time in millions of years this object has experienced significant heating. During its extensive interstellar voyage, 3I Atlas endured temperatures near absolute zero. With only the faint radiation from distant stars providing any energy, the transition from deep space cold to solar heating initiates complex chemical and physical processes. Subsurface ices begin sublimating, potentially unveiling fresh material unchanged since the comet's formation billions of years ago in another star system. Spectroscopic observations are already disclosing the composition of the escaping gases. These measurements will identify the molecules and compounds composing the comet's nucleus, offering direct samples of material from another planetary system. The brightness variations astronomers are tracking may reveal the nucleus's rotation and whether its surface possesses uniform composition. Some areas might be more active than others, generating jets of gas and dust as they face the Sun. This awakening provides a unique opportunity to study pristine material from beyond our solar system. The reddish glow enshrouding 3I Atlas narrates a story inscribed in cosmic dust, revealing secrets about its origin and its long interstellar journey. This color signature offers vital clues regarding the comet's composition and history. Observations from the Fox telescope north reveal the comet's coma exhibits a distinctly reddish hue, indicating the presence of complex organic compounds and dust particles. This coloration closely mirrors that of Borisov, the previous interstellar comet, suggesting similar formation processes in the outer regions of planetary systems. The dust released from the 3I Atlas nucleus contains information about conditions in its birth system billions of years ago. When planetary systems form, their outer regions become populated with icy bodies, rich in water, carbon dioxide, and organic molecules. These building blocks of planets and life become incorporated into comets during the chaotic early phases of system evolution. Spectroscopic analysis of the dust reveals specific wavelengths of light corresponding to compounds. Each molecule possesses a unique spectral fingerprint, enabling the identification of carbon monoxide, methane, and more complex organic species in the coma. The size and distribution of dust particles also furnish important information. Larger particles indicate recent activity from the nucleus, while smaller grains may have been altered by radiation during the long interstellar journey. The ratio between different-sized particles helps scientists estimate the comet's activity in its original system versus its current activity. Infrared observations will prove particularly valuable for studying the dust's thermal properties. The James Webb Space Telescope can detect heat radiation from dust grains, revealing their temperature, size, and composition. This cosmic dust represents some of the most pristine material we can study from another star system, carrying chemical signatures from a time and place billions of years and billions of light years distant from Earth. Next, we investigate why this visitor seems dramatically larger than previous interstellar objects. 3 Atlas marks a significant departure from our prior observations of interstellar visitors, especially concerning its potentially immense size. Current estimations propose this cosmic traveler could be 10 times larger than any previously detected interstellar object, fundamentally altering our comprehension of the types of objects regularly traversing between star systems. Preliminary brightness measurements assign 3I Atlas an absolute magnitude of approximately 11.9, which translates to a maximum potential diameter of around 24 kilometers, assuming it were a dark, inactive asteroid. However, given this object's clear status as an active comet, enveloped by a bright, reflective coma of gas and dust, the actual dimensions of its solid nucleus are anticipated to be considerably smaller than these initial estimations suggest. Even so, conservative calculations indicate 3 Atlas appears substantially larger than its interstellar predecessors. Oumuamua measured only a few hundred meters across at most, while comet Borisov's nucleus was estimated at just 400 to 500 meters in diameter. If present-size estimations prove accurate, 3 Atlas could represent a wholly distinct class of interstellar object. This dramatic size disparity raises profound questions about the processes expelling objects from their originating planetary systems. Larger objects necessitate significantly more energy to achieve the escape velocities required for interstellar journeys. The fact that such a massive body was accelerated to such extreme speeds suggests incredibly violent cosmic occurrences transpired in its natal system. The greater size also holds significant implications for the object's scientific value. Larger comets typically exhibit more diverse chemical compositions and retain more detailed records of their formation conditions. 3I Atlas may preserve pristine samples of material from multiple regions of its original planetary system, providing unprecedented insights into alien world formation. Precisely determining its size remains challenging because active comets are surrounded by expanding clouds of reflective dust, dramatically increasing their apparent luminosity. The true nucleus could be much smaller than current estimations suggest, concealed within the growing coma, rendering precise measurements extremely difficult with current observational techniques. Advanced radar observations might eventually yield more precise size measurements by penetrating the dusty coma to directly detect the underlying solid nucleus. The Arecibo Observatory's replacement facilities and other major radar installations are under consideration for this challenging, yet potentially rewarding, observational campaign. The James Webb Space Telescope's infrared capabilities offer another avenue for determining accurate size measurements. By detecting thermal emissions from the nucleus itself, astronomers can differentiate between heat emanating from the solid core and reflected sunlight from the surrounding dust cloud. Understanding the true size of 3I Atlas will assist astronomers in better modeling the population of interstellar objects and predicting the number of similar visitors we might expect to discover in the coming years. The discovery of 3 Atlas perfectly coincides with the dawn of a transformative era in astronomical observation, an era inaugurated by the recent commissioning of the Vera C. Rubin Observatory in Chile. This extraordinary facility promises to revolutionize our detection of interstellar objects, transforming them from rare, accidental finds into routine scientific observations. The Rubin Observatory stands as the most advanced sky survey system ever built, specifically engineered to repeatedly scan the entire southern sky every few nights for a full decade. Its colossal 3.2 gigapixel camera captures images encompassing 3.5 degrees of sky in a mere 15 seconds, a field of view wide enough to contain 7 full moons arranged side by side within a single frame. In its initial week of operation, the observatory uncovered over 200 previously unknown asteroids, vividly showcasing its remarkable capacity for identifying moving objects. This detection rate significantly surpasses the combined yearly discoveries of all other ground and space-based observatories, signaling a profound shift in our observational capabilities. Its automated systems can pinpoint potentially intriguing objects within minutes of image acquisition, comparing fresh observations with existing data to flag anything exhibiting movement, increased brightness, or unusual behavior. This rapid processing ensures that interstellar visitors like 3 Atlas would be detected and tracked from their very first appearance in our solar system. Current projections indicate that the Rubin Observatory will uncover between 1 and 10 interstellar objects annually once it achieves full operational capacity. This constitutes a dramatic escalation from the current rate of approximately 1 discovery every few years, potentially providing a consistent influx of cosmic visitors for in-depth study. The observatory's expansive field of view and rapid scanning capabilities will also mitigate the detection biases that nearly resulted in 3 Atlas going unnoticed. Even objects traversing densely populated star fields near the galactic center will be detectable, thanks to sophisticated image processing algorithms designed to discern subtle motion patterns. The facility's unparalleled data acquisition rate will generate roughly 20 terabytes of information nightly, necessitating advanced artificial intelligence systems to identify the most scientifically compelling targets amongst millions of routine observations. This technological revolution signifies the imminent end of the era, where interstellar visitors are considered rare, unexpected discoveries. Instead, these cosmic messengers will become frequent subjects of scientific inquiry, enabling astronomers to develop a comprehensive understanding of how planetary systems throughout the galaxy form, evolve, and ultimately release objects into interstellar space. A substantially enlarged statistical sample of interstellar objects will empower us to address fundamental questions concerning the structure and evolution of planetary systems orbiting diverse types of stars. The odyssey of 3I Atlas through interstellar space stands as one of the most extraordinary survival narratives in the known universe. For millions of years, this ancient comet has withstood conditions that would instantly obliterate most earthly materials. Yet it has emerged from this cosmic crucible largely unscathed, ready to unveil its story. During its protracted journey between star systems, 3I Atlas experienced temperatures approaching absolute zero, approximately -270 degrees Celsius. At such frigid extremes, most chemical reactions grind to a halt and materials become exceptionally brittle. The available thermal energy is so minuscule that even the movement of individual atoms within molecules slows to near stillness. The radiation environment of interstellar space presents equally formidable survival challenges. High-energy cosmic rays, propelled to immense velocities by distant supernovae and other cataclysmic cosmic events, relentlessly bombarded the comet's surface. These energetic particles can shatter complex molecular structures and gradually alter the chemical makeup of exposed materials over geological timescales. Galactic cosmic radiation encompasses everything from individual protons and electrons to heavy atomic nuclei, traveling at significant fractions of the speed of light. When these particles strike the comet's surface, they generate cascades of secondary radiation that can penetrate several meters into solid ice and rock, potentially modifying subsurface materials only revealed when the comet reactivates. Despite these harsh conditions, 3I Atlas appears to have remarkably preserved its structural integrity and chemical composition. Its ability to outgas normally upon solar heating indicates that its internal ice deposits remain largely unaffected by radiation damage or thermal cycling effects. This comet's ability to survive this cosmic voyage intact provides invaluable insights into the resilience of materials under extreme conditions. Understanding how complex molecules and ice structures endure millions of years of radiation exposure holds significant implications for astrobiology and the potential preservation of organic compounds in space. Theoretical models suggest that objects like 3I Atlas can retain viable chemical compositions for tens of millions of years during interstellar transit, potentially transporting complex organic molecules and even simple biological precursors between star systems. This possibility raises intriguing questions about whether life itself might occasionally disperse throughout the galaxy or via interstellar objects. The surface layers directly exposed to radiation during the journey may have developed protective crusts that actually shielded underlying materials from further damage, effectively creating natural time capsules of pristine, ancient material. The incoming trajectory of 3I Atlas offers captivating clues about its ultimate origins, potentially enabling astronomers to trace this cosmic traveler back through millions of years of galactic motion to pinpoint its likely birthplace. This cosmic investigation stands as one of the most ambitious forensic endeavors ever undertaken in the realm of space science. The comet arrived from the direction of Sagittarius, specifically from the galactic disk region, the home to the majority of stars within our Milky Way galaxy. This directional data, coupled with its extraordinary velocity and computed trajectory, indicates that 3I Atlas has journeyed through space for several million years since its forceful ejection from its parent system. Reconstructing its path necessitates accounting for the intricate gravitational influences encountered during its protracted voyage. Our galaxy rotates like a colossal pinwheel, with various regions moving at varying speeds relative to one another. Stars nearer the galactic center orbit faster than those in the outer regions, resulting in a dynamic environment where stellar neighborhoods are in constant flux. During its multi-million-year odyssey, 3I Atlas would have traversed regions containing hundreds or thousands of diverse star systems. Each close encounter with a massive object would have subtly altered its trajectory, rendering precise backtracking extremely difficult, though not insurmountable, with sophisticated computer modeling. The comet's present velocity vector, when projected backward through galactic space, while considering known stellar movements, suggests it may have originated from a region significantly closer to our solar system several million years ago. The relative motion of star systems means that 3I Atlas's birthplace star could now be situated in an entirely different part of the galaxy. Advanced computer simulations can model the gravitational environment of the local galactic neighborhood over extensive time periods, incorporating data regarding stellar positions, masses, and velocities to reconstruct feasible trajectories. These computations demand enormous computational resources, but possess the potential to identify candidate star systems appropriately positioned to eject an object along 3I Atlas's observed path. Several research teams have already commenced this intricate analysis, using data from the European Space Agency's Gaia spacecraft, which has precisely measured the positions and motions of over 1 billion stars across our galaxy. This unparalleled stellar catalogue provides the foundation for tracing interstellar objects back to their points of origin. The investigation confronts substantial challenges due to measurement uncertainties and the chaotic nature of gravitational interactions over such extended time spans. Minor errors in initial conditions can yield drastically different conclusions about the object's origin, necessitating meticulous statistical analysis of multiple potential scenarios. Successfully pinpointing 3I Atlas's birth system would represent a significant advancement in our comprehension of planetary system evolution and the exchange of material between different star systems throughout the galaxy. The exceptional speed of 3I Atlas narrates a tale of immense past violence within a distant star system. Objects do not naturally attain the extraordinary velocities required for interstellar journeys through gradual evolutionary processes. Instead, they necessitate sudden, potent gravitational encounters, instantly transforming ordinary comets into cosmic projectiles hurtling across the galaxy. Several plausible scenarios could account for the enormous energy needed to propel 3I Atlas to its present 66 kilometers per second velocity. The most probable explanation involves close encounters with massive bodies during the chaotic early development of its natal planetary system, a time when large planets were still migrating, and interactions between multiple celestial bodies created dynamically unstable conditions. Gravitational slingshot effects around giant planets can accelerate smaller objects to exceptionally high velocities under suitable conditions. When a comet approaches a massive planet on a precisely angled trajectory, it can gain tremendous energy from the planet's orbital movement, effectively appropriating momentum from the far more massive world and converting it into escape velocity. Multiple consecutive encounters with different planets can produce even more dramatic acceleration effects, each gravitational interaction adding further energy to the object's motion. Computer simulations demonstrate that objects can occasionally achieve hyperbolic escape trajectories through a series of precisely timed planetary encounters occurring during periods of orbital instability. Another possibility involves stellar close encounters, where a passing star approaches sufficiently close to gravitationally disrupt the outer regions of 3I Atlas's birth system. When two star systems pass within a few light years of each other, their gravitational fields can interact, flinging objects from the outer reaches of planetary systems into interstellar space at tremendous velocities. The most spectacular ejection mechanism involves stellar evolution itself. When massive stars reach the end of their lives and undergo supernova explosions, the tremendous energy released can accelerate nearby objects to significant fractions of the speed of light. While 3I Atlas's velocity is far below such extreme levels, asymmetric supernova explosions or interactions with stellar remnants could potentially provide the requisite acceleration. Binary star systems offer further ejection possibilities. When two stars orbit in close proximity, objects in the outer regions of such systems can experience complex gravitational effects that sometimes result in hyperbolic ejection trajectories. The gravitational interplay between multiple massive objects creates chaotic dynamics that can unpredictably accelerate smaller bodies. Recent theoretical work suggests that planetary system instabilities during the late heavy bombardment period, similar to what our own solar system experienced billions of years ago, routinely eject substantial numbers of objects into interstellar space. Understanding these ejection mechanisms aids astronomers in estimating the number of interstellar objects traversing our galaxy at any given time. 3I Atlas signifies far more than just another intriguing astronomical object. Acting as a direct physical sample from a wholly different planetary system, this interstellar comet delivers invaluable data on planetary formation and evolution around distant suns. It presents a singular opportunity to investigate extraterrestrial chemistry and geology without the insurmountable hurdle of interstellar travel. Comets originate in the frigid outer reaches of planetary systems, where temperatures are sufficiently low to freeze water, carbon dioxide, methane, and other volatile substances into solid ice. During the chaotic early stages of planetary system genesis, they incorporate materials from diverse sources, dust grains from the original stellar nebula, processed matter from the inner system, and organic compounds synthesized through various chemical reactions. The chemical makeup of 3I Atlas's nucleus and coma will unveil fundamental details about the elemental abundances and isotopic ratios within its natal system. Different stars possess distinct metallicities and chemical signatures, reflecting their formation histories and stellar evolution, leaving unique fingerprints preserved in objects formed around them. Spectroscopic analysis can pinpoint specific molecules and compounds released from the comet's nucleus as it nears the Sun. Water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and more complex organic molecules each exhibit characteristic spectral signatures, enabling astronomers to determine not only constituent elements, but also their chemical bonding. Isotopic ratios provide especially valuable insights into stellar nucleosynthesis and galactic chemical evolution. The relative abundances of different isotopes of elements such as carbon, nitrogen, and oxygen can reveal details about the stellar environment where 3I Atlas formed and whether its parent system underwent unusual stellar evolutionary events. Organic compounds are particularly intriguing because they offer clues about the potential for life in other planetary systems. While 3I Atlas likely formed too distantly from its host star to have directly supported life, it might contain complex carbon-based molecules representing the fundamental building blocks from which life could potentially arise under more favorable circumstances. The dust particles emanating from the comet's nucleus offer another path to studying alien materials. These microscopic grains can retain information about high-temperature processes during the early formation of the planetary system, including condensation sequences and thermal processing in the inner regions before outward transport. Advanced laboratory techniques, if samples were attainable, would permit incredibly detailed analysis of individual dust grains and ice crystals. However, even distant spectroscopic observations can yield remarkably precise information about the composition and structure of materials from another star system. Comparing 3I Atlas's composition with objects in our solar system will highlight similarities and differences, reflecting the universal and unique aspects of planetary system formation and chemical evolution. A profound sense of urgency grips the global astronomical community. Time is rapidly dwindling for humanity's investigation of 31/Atlas. This interstellar visitor presents a singular opportunity to study pristine material from another star system, but the window for comprehensive observation is closing faster than many scientists deem desirable. The primary hurdle lies in 31/Atlas's orbital mechanics and its relation to Earth's solar orbit. As the comet approaches perihelion in late October, it will draw increasingly closer to the Sun's apparent position in our sky, rendering telescopic observations progressively more challenging due to solar glare and interference. Ground-based observatories face the added limitation that 31/Atlas must be observed during nighttime hours, when the object is above the horizon and the sky sufficiently dark. As the comet's apparent position nears the Sun, the nightly observing window shrinks, eventually vanishing altogether when the object passes behind the Sun from Earth's perspective. This situation is further complicated by seasonal effects, and the geographic distribution of major observatories. Northern Hemisphere facilities are losing access to 31/Atlas as its declination shifts southward, while Southern Hemisphere observatories contend with escalating solar interference as the object nears perihelion. Space-based telescopes offer certain advantages over ground-based facilities, primarily the capacity to observe during Earth's daytime. However, even these space observatories must carefully avoid pointing too near the sun to prevent instrument damage, limiting their ability to track 31/Atlas during its closest solar approach. The James Webb Space Telescope, situated at the L2 Lagrange point, enjoys a more favorable geometric arrangement for continued observation later in the comet's approach. Yet it too faces restrictions on how close to the sun it can safely point its instruments. Mission planners are meticulously optimizing observing schedules to maximize scientific yield while safeguarding this invaluable facility. After disappearing behind the sun in late September, 31/Atlas will remain unobservable for several months before reappearing in December on the opposite side of our star. By then, the comet will be rapidly receding from the inner solar system, dimming and becoming less active as it retreats into the cold expanse of space beyond. This December reappearance offers a second observational chance, but the comet will be considerably fainter and less active than during its inbound approach. Many detailed spectroscopic measurements demanding high signal-to-noise ratios may prove impossible once the object begins its outbound trajectory. This temporal constraint means the next few months represent humanity's only realistic opportunity for comprehensive studies of this remarkable interstellar visitor. The James Webb Space Telescope stands as humanity's most powerful instrument for investigating 3I/Borisov, providing unparalleled means for analyzing the thermal properties and chemical makeup of this interstellar visitor. Webb's advanced infrared instruments can detect heat radiation and molecular signatures entirely imperceptible to optical telescopes, thus opening entirely new avenues for understanding extraterrestrial materials. Infrared observations offer crucial advantages in studying active comets, as many significant molecular species emit characteristic radiation at infrared wavelengths. Water vapor, carbon monoxide, carbon dioxide, methane, and numerous organic compounds all possess distinctive infrared spectral signatures, which Webb's sophisticated instruments can detect and analyze with extraordinary precision. The telescope's near-infrared spectrograph can simultaneously observe hundreds of different wavelengths, generating detailed spectral maps that reveal the presence and abundance of numerous chemical species within 3I/Borisov's coma. This capability allows astronomers to compile comprehensive chemical inventories that would be impossible using any other existing facility. Webb's mid-infrared instrument offers complementary capabilities for studying the thermal properties of dust particles released from the comet's nucleus. By measuring the infrared heat radiation emitted by microscopic grains, astronomers can determine their composition with exceptional accuracy. These thermal measurements also furnish insights into the comet's internal structure and activity patterns. Different regions of the nucleus may heat at varying rates as the comet approaches the sun, creating temperature variations that can reveal information about the object's rotation, surface composition, and subsurface thermal properties. One of Webb's most valuable assets involves detecting extremely faint infrared emission lines from trace species potentially present in minuscule quantities within the comet's atmosphere. These measurements could potentially identify complex organic molecules or unusual isotopic ratios, offering clues about exotic chemical processes in its originating system. The telescope's exceptional stability and sensitivity allow for time series observations, tracking how 3I/Borisov's activity changes as it nears the Sun. These temporal measurements can reveal how different chemical species respond to increasing solar heating, providing insights into the nucleus's physical structure and composition. Webb's infrared capabilities also enable observations that penetrate the dusty coma to study thermal emission from the nucleus itself. This direct view of the solid core can provide size estimates and surface temperature measurements impossible to obtain using optical wavelengths, where dust scattering dominates the observed brightness. Coordinated observations using Webb's multiple instruments can create comprehensive portraits of 3I/Borisov, combining chemical analysis, thermal mapping, and temporal monitoring into unified scientific datasets. These integrated measurements will provide the most detailed characterization ever accomplished for an interstellar object. The James Webb Space Telescope's location at the L2 Lagrange point offers a geometrically advantageous vantage point for prolonged observation of 3I/Atlas as it nears and passes perihelion. The subtle fluctuations in 3I/Atlas's brightness as it rotates function as a cosmic barcode, encoding vital information about its form, surface properties, and internal structure. These meticulously measured light curves represent one of the most accessible methods for astronomers to characterize the physical attributes of this distant interstellar visitor, even using ground-based telescopes. As 3I/Atlas spins on its axis, different sections of its surface alternately face towards and away from the Sun and Earth, producing cyclical alterations in the reflected sunlight reaching our telescopes. The precise pattern of these brightness variations hinges on the object's rotation rate, axial orientation, surface compositional uniformity, and overall shape. Spherical objects generate relatively modest brightness variations because their projected area remains almost constant irrespective of viewing angle. However, elongated or irregularly shaped objects can exhibit dramatic brightness changes as they present different cross-sections to observers, potentially fluctuating by factors of several magnitudes during a single rotational period. The rotation period itself offers insights into the object's structural integrity and formative history. Rapidly spinning objects must possess considerable cohesion to prevent disintegration under centrifugal forces, while slowly rotating bodies may suggest loose gravitational binding or a recent collisional history that disrupted their angular momentum. 3I/Atlas presents a challenge for light curve analysis because its developing coma introduces additional brightness contributions that change independently of the nucleus rotation. The expanding cloud of gas and dust reflects sunlight and emits its own thermal radiation, potentially obscuring the subtle periodic signals from the underlying solid body. Sophisticated photometric techniques can partially disentangle these diverse brightness contributions by observing at multiple wavelengths simultaneously. The nucleus surface reflects sunlight with different spectral characteristics than the surrounding dust cloud, enabling skilled observers to isolate the rotational signature through careful spectral analysis. Professional and amateur astronomers globally are conducting coordinated photometric campaigns to continuously measure 3I/Atlas's brightness variations over extended periods. These collaborative efforts provide temporal coverage unattainable by any single observatory, ensuring that rotation periods spanning hours or days can be accurately determined. The brightness measurements also unveil information about surface compositional heterogeneity. If different regions of the nucleus possess varying reflectivity properties due to compositional differences or varying degrees of dust coverage. These variations will create distinctive patterns in the observed light curves. Comparing 3I/Atlas's rotation properties with those of comets within our own solar system can reveal similarities and differences that reflect universal versus unique facets of comet formation and evolutionary processes. These comparisons aid astronomers in understanding whether interstellar objects represent fundamentally distinct populations or simply displaced versions of familiar solar system bodies. Long-term monitoring throughout the comet's approach to perihelion will track how escalating solar heating impacts the rotation properties, potentially revealing asymmetric outgassing that could alter the spin rate or orientation over time. Despite its immense speed and extraterrestrial origins, Comet 3E Atlas presents absolutely no threat to Earth or any other planet within our solar system. Calculations of the comet's trajectory, performed with exceptional precision, definitively confirm its safe passage through the inner solar system. It will not approach our planet or disrupt any established orbital patterns. The comet's closest approach to Earth will occur on December 17th, when 3E Atlas reaches a distance of approximately 2.4 astronomical units from our planet. This equates to roughly 360 million kilometers, or about 2.5 times the Earth-Sun distance. At this range, the comet will appear as merely an extremely faint pinpoint of light, requiring sophisticated telescopes for detection. Even at its closest approach to the Sun in late October, 3E Atlas will maintain a safe distance of 1.4 astronomical units, positioning it well within Mars's orbit but far from Earth's orbital path. This perihelion distance ensures substantial solar heating, driving observable cometary activity while guaranteeing its complete harmlessness to inner solar system dynamics. The comet's hyperbolic trajectory guarantees it will never return to pose a threat to Earth or any other celestial body in our solar system. Following its fleeting visit to the inner regions, 3E Atlas will continue its outward trajectory into the vastness of space, disappearing from our cosmic neighborhood forever. Its orbital energy far surpasses what would be required for capture into a bound solar orbit. Planetary defense organizations worldwide concur that 3E Atlas poses absolutely no impact risk. The European Space Agency's Near-Earth Object Coordination Center and NASA's Planetary Defense Office both independently verified these safety calculations, employing multiple computational methods and observational datasets. The comet's relatively large size, while scientifically fascinating, does not increase its danger. Large objects on safe trajectories remain safe, irrespective of their size, and 3E Atlas's path will not bring it near any inhabited worlds or crucial space-based infrastructure. Ground-based radar systems, typically used to track potentially hazardous asteroids, have also attempted to observe 3E Atlas, although its great distance and rapid motion make radar detection exceptionally challenging. These observations further confirm the trajectory calculations, while potentially revealing surface properties and rotational characteristics. These safety assurances enable the global astronomical community to fully concentrate on the scientific opportunities offered by this remarkable celestial visitor, without concerns about planetary protection or impact mitigation. Research teams can dedicate their complete attention to understanding what 3E Atlas reveals about interstellar objects and alien planetary systems. Public education initiatives highlighted both the scientific excitement and the complete safety of this cosmic encounter, fostering support for continued astronomical research while mitigating unnecessary anxieties about celestial threats. The combination of this object's scientific importance and confirmed safety makes 3I/Atlas an ideal ambassador for public engagement with space science. The discovery and characterization of 3I/Atlas showcases the remarkable power of citizen science in modern astronomy, demonstrating how passionate amateur researchers can make crucial contributions to cutting-edge scientific investigations. This collaborative approach represents a fundamental shift in how astronomical discoveries unfold, democratizing participation in cosmic research beyond traditional academic institutions. Sam Dean's discovery of pre-discovery observations exemplifies the valuable role dedicated amateurs can play in professional research. Working from his home computer without formal institutional affiliation, Dean systematically searched massive archival datasets that professional astronomers had not yet fully analyzed. His meticulous work extended 3I/Atlas's observational timeline by crucial weeks, dramatically improving orbital calculations. This citizen science approach's success reflects the increasing availability of professional-quality astronomical data through online archives and public databases. Major survey projects like ATLAS, the Zwicky Transient Facility, and others routinely make their observations publicly accessible, creating opportunities for anyone with sufficient dedication and computational skills to make genuine discoveries. Amateur astronomers, equipped with modest but sophisticated equipment, are contributing valuable photometric observations of 3I/Atlas from locations around the globe. These distributed measurements provide temporal coverage that no single professional observatory could achieve alone, enabling continuous monitoring of brightness variations and rotation properties. The democratization of telescope access through remote observing systems allows amateur researchers to use professional-grade instruments located in ideal dark sky locations. Services like itelescope.net enable citizen scientists to capture high-quality images and spectroscopic data that contribute meaningfully to scientific understanding of interstellar objects. Social media platforms and online astronomy communities facilitate rapid information sharing and coordination among amateur observers worldwide. Within hours of 3I/Atlas's discovery announcement, amateur astronomers were sharing observation plans, coordinate information, and preliminary results through networks spanning multiple continents and time zones. The collaborative spirit extends beyond simple data collection to include sophisticated analysis techniques. Amateur researchers are developing innovative software tools for photometric analysis, astrometric measurements, and spectroscopic data reduction that rival capabilities available to professional institutions. Educational institutions are increasingly recognizing the value of citizen science projects for engaging students in authentic research experiences. High school and undergraduate astronomy programs are incorporating 3I/Atlas observations into their curricula, providing students with opportunities to contribute to active scientific investigations while learning fundamental research techniques. The success of amateur contributions to 3I/Atlas research helps validate the citizen science model for future astronomical discoveries. As automated sky surveys discover increasing numbers of interesting objects, the astronomical community will increasingly rely on distributed networks of amateur researchers to provide detailed follow-up observations and analysis. This collaborative approach maximizes the scientific return from limited professional telescope resources while engaging broader public audiences in the excitement of astronomical discovery. The successful identification and characterization of 3I/Atlas marks a phenomenal achievement, pushing the boundaries of current astronomical capabilities. This interstellar visitor arrived at the very edge of what our existing telescope networks and detection systems can reliably observe, showcasing both the impressive potential and inherent limitations of 21st-century space surveillance technology. At magnitude 18.8, 3I/Atlas appears roughly 2.5 million times dimmer than Polaris, the North Star, demanding sophisticated equipment and exceptionally favorable observing conditions for successful detection. Most amateur telescopes cannot detect objects dimmer than magnitude 15 or 16 under typical circumstances, placing this interstellar object far beyond the reach of casual astronomical observation. The initial discovery by the Atlas survey system demonstrates the remarkable sensitivity of modern automated sky monitoring programs. Atlas routinely detects objects near magnitude 19, representing the current practical limit for wide-field survey telescopes, which must efficiently cover vast swathes of the sky while maintaining reasonable exposure times. Follow-up observations using larger telescopes extend detection limits even further, with facilities like the Very Large Telescope capable of detecting objects several magnitudes fainter than survey systems. However, detailed spectroscopic analysis requires objects to be considerably brighter than the detection threshold, limiting the scientific information extractable from exceptionally faint targets. The geometric context of 3I/Atlas's discovery presented unique difficulties because the object appeared against the densely populated star fields of the galactic center region. This background complexity significantly complicates automated detection algorithms that rely on identifying moving objects against relatively sparse stellar backgrounds. Weather conditions, atmospheric turbulence, and light pollution all significantly affect the ability to detect and track faint objects such as 3I/Atlas. Professional observatories invest substantial resources in site selection and environmental control systems to maximize their sensitivity to faint cosmic targets. The rapid movement of 3I/Atlas across the celestial sphere presents additional technical hurdles for obtaining detailed observations. Long exposure times, normally employed for studying faint objects, become problematic when targets move significantly during the exposure, requiring specialized tracking techniques and shorter integration times, which reduce overall sensitivity. Collaborative observations by multiple telescopes help mitigate some of these limitations by combining data from various facilities to achieve improved signal-to-noise ratios and more complete coverage. International cooperation becomes crucial for maximizing scientific yield from challenging observational targets. The detection of 3I/Atlas also emphasizes the importance of continued technological advancement in astronomical instrumentation. Next-generation survey systems and space-based observatories will dramatically enhance our capacity to detect and study faint interstellar visitors, potentially revealing a far larger population of cosmic wanderers than currently possible. Understanding detection limits helps astronomers estimate the number of similar objects possibly traversing our solar system undetected at any given moment. The discovery of Oumuamua prompts profound questions. How many similar interstellar objects silently traverse our solar system, undetected by current technology? Theoretical models posit a far greater abundance of these cosmic wanderers than our observations suggest. Statistical analysis of the three confirmed interstellar objects, Oumuamua, 2I/Borisov, and 1I/Oumuamua, indicates these represent merely the tip of a much larger iceberg. For every interstellar visitor, bright and favorably positioned for detection, dozens or hundreds likely pass unnoticed. Detection bias strongly favors objects passing relatively close to Earth, arriving from convenient celestial directions. Interstellar visitors traversing our solar system's outer regions approaching from less observable angles, or arriving during periods of Earth-based telescope unavailability, remain completely invisible to our detection networks. Current estimates suggest thousands of interstellar objects, larger than a few meters across, might reside within our solar system at any given time. The vast majority remain undetectable due to their small size, immense distance, or unfavorable observational geometry from Earth. The size distribution of interstellar objects likely mirrors that of asteroids and comets in our own solar system, vastly more small objects than large ones. While Oumuamua, an unusually large specimen, aided its own detection, the cosmic population probably consists primarily of much smaller bodies, currently undetectable by our technology. Improvements in survey capabilities over the next decade will dramatically increase interstellar object detection rates. The Vera C. Rubin Observatory alone is expected to discover between 1 and 10 interstellar visitors annually at full operational capacity, a tenfold or greater increase over past rates. Future space-based survey systems will further revolutionize detection by eliminating atmospheric limitations and providing continuous sky coverage. These advanced facilities will detect much fainter objects across broader sky areas, potentially revealing the true abundance of cosmic wanderers. This hidden population of interstellar objects may include representatives from diverse planetary systems throughout our galactic neighborhood. Each object carries unique information about its origin system, offering opportunities to study the chemical compositions and formation processes of worlds we cannot directly observe. Long-period surveys, spanning decades, will be necessary to construct comprehensive statistical samples of interstellar objects and understand their diversity. The accumulated data will assist astronomers in understanding ejection mechanisms, travel times, and the exchange of material between different star systems. Understanding the true population of interstellar visitors holds significant implications for planetary defense, astrobiology, and our comprehension of planetary system evolution and interaction throughout the galaxy. 32I Atlas serves as a direct example of the fundamental building blocks that formed planets around a distant star, offering unparalleled insights into whether the processes that created worlds in our solar system represent universal patterns or unique local events. This cosmic comparison unveils profound truths about planetary formation across the galaxy. Spectroscopic analysis of 32I Atlas's coma reveals its chemical composition, providing direct measurements of elemental abundances in another star system. These observations enable astronomers to compare the raw materials available for planet formation around different types of stars with varying ages, masses, and metallicities. Preliminary findings suggest 32I Atlas contains water, carbon monoxide, and other volatiles in proportions generally similar to comets in our own Kuiper belt. This similarity supports theoretical models, suggesting that the basic chemistry of planetary formation follows universal physical laws, irrespective of the specific stellar environment. However, subtle differences in isotopic ratios and trace element abundances might reveal significant variations in stellar nucleosynthesis processes or galactic chemical evolution. The precise ratios of different isotopes of carbon, nitrogen, and oxygen can provide insights into the stellar generations that contributed material to 32I Atlas's birth system. The organic compounds detected in the comet's atmosphere offer particularly valuable insights into prebiotic chemistry in extraterrestrial environments. Complex carbon-based molecules form through various processes during planetary system evolution, and their presence or absence in interstellar objects reveals information about the potential for life in diverse cosmic environments. Dust grain analysis provides complementary information about high-temperature processes that occurred during the early formation of 32I Atlas's birth system. These microscopic particles preserve records of condensation sequences, thermal processing, and dynamical mixing that shape the distribution of materials throughout the original planetary disk. Comparing 32I Atlas with meteorites and comets from our solar system reveals both similarities and differences that illuminate the diversity of planetary system formation processes. Universal aspects reflect fundamental physics and chemistry, while unique characteristics reveal how local conditions influence world building. The size and activity level of 32I Atlas suggest it formed in the outer regions of a planetary system similar to our own, where temperatures were sufficiently low for volatile compounds to condense into solid form. This environmental similarity bolsters the notion that habitable zone planets may be common throughout the galaxy. Understanding the relationship between stellar properties and the composition of ejected objects helps astronomers predict what types of materials might be available for planet formation around different categories of stars. This information is crucial for evaluating the potential habitability of exoplanetary systems detected by survey missions. The accumulation of data from multiple interstellar objects will eventually enable comprehensive statistical comparisons between different stellar environments and their associated planetary building blocks. The discovery of 3 Atlas signifies far more than a noteworthy astronomical event. It ushers in a revolutionary era of space exploration. Interstellar objects, acting as natural probes, now deliver samples and data from distant realms directly to Earth, fundamentally altering our galactic investigations and self-perception. This successful identification and analysis of 3 Atlas proves our technology has reached a crucial juncture, enabling routine study of interstellar objects. Advanced automated survey systems, sophisticated spectroscopic instruments, and globally coordinated observation networks provide the means to fully exploit the scientific potential of these cosmic messengers. Future interstellar visitors will benefit from increasingly powerful observational capabilities as next-generation facilities, such as the Vera Rubin Observatory, the Extremely Large Telescope, and advanced space-based observatories, come online within the next 10 years. These will dramatically enhance our ability to detect, track, and analyze objects from other star systems with unprecedented detail and accuracy. Each new interstellar object will provide vital data points, enriching our understanding of planetary system formation, stellar evolution, and galactic chemical evolution. Observations from dozens or even hundreds of these cosmic visitors will eventually permit comprehensive statistical analyses of conditions throughout our galactic neighborhood. The diversity of interstellar objects likely mirrors the incredible variety of planetary systems within the Milky Way galaxy. Some visitors might originate from systems dominated by gas giants, others from regions teeming with rocky worlds, still others from environments unlike anything within our solar system. Each messenger carries unique information about its point of origin. Advanced propulsion concepts currently under development may eventually enable robotic missions to intercept and study interstellar objects as they traverse our solar system. Such missions could return physical samples to Earth for thorough laboratory analysis, offering unparalleled insight into extraterrestrial materials and chemistry. The detection of biosignatures or complex organic molecules in interstellar objects would constitute one of humanity's most profound discoveries, potentially proving the existence of life elsewhere in the galaxy. Even simple organic compounds would demonstrate the widespread presence of life's chemical precursors throughout cosmic environments. International collaboration in interstellar object research is establishing data sharing and observation coordination frameworks to benefit future discoveries. These cooperative networks ensure humanity's response to cosmic visitors maximizes scientific yield while incorporating diverse global perspectives into the research process. Educational programs inspired by interstellar objects are fostering a new generation of scientists and engineers who will develop even more advanced techniques for studying these cosmic messengers. Student participation in actual research projects provides genuine experiences that inspire continued engagement with space science and exploration. 3 Ayatollahs and its successors serve as potent symbols of humanity's ever-expanding cosmic comprehension, a constant reminder that our solar system resides within a vibrant galactic neighborhood, a region where the exchange of matter and information between star systems is commonplace. These interstellar travelers forge a direct link between us and the wider universe, connecting us to our shared cosmic legacy. The future holds the promise of even more extraordinary discoveries as our detection capabilities advance, transforming interstellar visitors from rare, unexpected occurrences into routine subjects of scientific scrutiny. The passage of 3I Atlas through our solar system narrates a profound tale extending far beyond a single cosmic wanderer. This remarkable object, hurtling through space at unprecedented speeds, along the most extreme trajectory ever documented, provides our initial glimpse into a new epoch of interstellar science, an era where the universe itself delivers its secrets directly to our doorstep. From its near escape from detection, while obscured within the dense star fields of the galactic center, to the collaborative efforts of citizen scientists who lengthened its discovery window, 3I Atlas exemplifies both the challenges and opportunities defining 21st century astronomy. The global collaborative effort to investigate this visitor before its permanent departure showcases humanity at its scientific zenith, a unified endeavor to unlock cosmic enigmas. The truly revolutionary nature of this discovery lies not solely in what we have learned, but in what it portends for the future. The Vera Rubin Observatory and forthcoming generations of survey systems will soon transform infrequent interstellar visitors into routine scientific opportunities, granting us regular access to matter and information originating from distant worlds. 3I Atlas carries within its ancient nucleus and developing coma the chemical fingerprints of another star system, offering direct samples of alien world-building materials that would be utterly unreachable through conventional space travel methods. Each spectroscopic measurement and photometric observation contributes vital data to our understanding of planetary system formation and evolution across the galaxy. As this cosmic messenger concludes its fleeting visit to our solar system and departs into the vast expanse of interstellar space, it leaves behind a transformed astronomical community, one equipped with enhanced capabilities, a deepened understanding, and heightened anticipation for future breakthroughs. The age of interstellar object science has undeniably commenced. While the pursuit of 3I Atlas may be drawing to a close, the grander journey of cosmic exploration presses